G'day! Today we're going to be taking a look at another Bob's Fury Homebrew update. As you might be able to tell from the image in the background, I've got an EGA graphics to work, which is very exciting. So let's take a quick look at how EGA works before we take a look at some code running.
EGA is hard to code for because of how the video memory is arranged. It's divided up into sections called planes, which each represent a single colour channel that contributes to what is displayed. The colour channels are red, green, blue, and intensity. Each plane is arranged like a normal linear frame buffer, only with 1 bit per pixel. You can think of each plane as a monochrome image, all 4 combined describing the colour image. Manipulating pixels in these planes requires a lot of masking and shifting, as each byte contains 8 pixels. Fortunately, EGA includes some nifty logic to make this easier. This logic is arranged into a simple pipeline controlled by registers. Each plane has its own pipeline, 8 bits wide, each one with the potential to operate in parallel. In practice, this is hard, as most features of the pipelines share the same control registers, with some exceptions. Fortunately, you can choose which ones to enable, so it's possible to operate on a single plane if needed. The cost of this arrangement is the CPU cannot directly access the video RAM. Additionally, there are read and write modes that configure the logic differently. Some examples follow. Write mode 0 is the default. Data arrives from the CPU and is shifted in the barrel shifter to align with the intended draw location. This data is passed to the ALU, which may simply pass the data through or use a logical operation such as OR, AND, XOR or NOT to modify the data. Latch data is used for the other operand. The last step, the bit mask, is a multiplexer that selects whether a bit comes from the ALU or the latch. This allows us to mask some pixels off to preserve their data. The latch is simply 8 bits of memory. It is loaded with data from the plane when the CPU performs a read operation. Some things to note. All the plane pipelines get exactly the same data from the CPU, so generally you'd only update one plane at a time in this mode for colour images. Write mode 2 configures things slightly differently. The pipelines themselves retain the same structure, but are fed differing data depending on what is written by the CPU. The data fed in is either all ones or all zeros depending on a bit in the CPU data. Plane 0 uses the least significant bit, plane 1 uses bit 1, and so on. Essentially, the data written by the CPU is the colour data combined instead of being divided into planes. The advantage of this mode is using all the pipelines in parallel to update up to 8 pixels per write. The downside is you can only draw with one colour at a time. The process the CPU follows to update the video data remains the same for each write mode. Firstly, you need to set up the logic for your drawing operation. Modifying registers can be slow, so it's a good idea to minimise changes as much as possible. Then you need to determine the address in VRAM you wish to update. Since all the planes share the same address space, it's fairly straightforward. Before writing new data, it's important to do a dummy read to ensure the latches are loaded with the data that will be needed. Then you can write the new pixel data that will be processed by the pipelines. For drawing an image, I used write mode 0, as each pixel is likely to be a different colour. I need to write different data to each plane. This means I need to update each plane separately, and thus need to store image data for each of them. It's basically like drawing 4 monochrome images to the same location within different frame buffers. I've simplified the pipelines and process a little, as I didn't use all the features in my code. If you're interested in learning more about EGA, the book by Richard Ferrero was recommended to me. It has a comprehensive description of the hardware with some sample code. It was extremely helpful. Michael Abrash's book is also an interesting read and has useful information about 16-colour graphics, but not specifically for the EGA. Still, it's a good read and I'd recommend it as well. Here is my EGA code emulated on 86box, set up as a 20MHz 386. Performance testing has been difficult for the EGA code, with different results depending on circumstances. Code running under 86box seems to have roughly performance parity for image drawing, but under DOSBox my code is faster, and on the Microbyte 386 it is faster, but by a smaller margin. So I'm not really sure what to think yet. I might need to optimise my code a bit more to see if I can squeeze a little bit more out of it. Either way, both EGA implementations are not fast enough to run on the oldest of machines. I'm guessing it will likely require a 286 to be playable still. This is hardly surprising as I can't think of any EGA games that would work on something slower. The new code has some other advantages as well other than performance. For instance, the text is now drawn with the same aspect ratio and relative size as all of the other graphics modes. This gives it a little bit more consistency and makes things look a bit better.
So the EGA code went really well. The one thing was that I discovered in my working with it that my line drawing benchmarks were completely off. And I discovered from fixing that all my line drawing code is horrendously slow. Now this is a problem because all my line drawing code is used to draw the fonts for the text on screen. I've essentially written my own font drawing algorithm that takes the straight font from the BGI and draws it through my graphics libraries. Now, the problem isn't so much with the code that interprets the characters and draws the lines, it's with the line drawing itself. And what this has meant is that on slower machines, any kind of text at all takes longer to update than it should. So I've spent a little bit of time updating the line drawing code.
Drawing lines on PCs can be a little tricky. The older CPUs are pretty slow if you try to do this with floating point numbers. Fixed point also has significant issues that make it slower. Luckily for us, there is a nifty algorithm that solves the problem using only signed integers. This is called the Bresenham's line drawing algorithm. Here's a simplified sample of what it looks like from Wikipedia. This one only handles lines that are mostly horizontal and sloping downwards. It's pretty straightforward to make something based on this that can draw arbitrary lines. I had already written code for this algorithm, but it performed poorly, mostly because I had used the putPixel routine and used Pascal code instead of optimizing things with assembly. So I decided to refactor the line drawing into assembly. VGA mode 13 hex was the easiest to write as it doesn't require too much work to draw a pixel or calculate memory offsets. It was pretty straightforward. CGA isn't so straightforward due to having 4 pixels stored in each byte and having different banks of memory for odd and even rows of pixels. To reduce the number of reads and writes to video memory, I took the approach of building a byte worth of pixels in a register and only writing that byte to the screen once it's completed. EGA has a similar problem, but with that nifty update logic and write mode too, you just have to build up a mask for the pixels you want to update for each byte. I haven't converted this one to assembly yet. The Pascal code isn't fast, but works well enough to play the game. Interestingly, the BGI performs quite well drawing lines to the EGA, doing significantly better than CGA and VGA modes. It seems Borland put a lot of effort into the EGA VGA driver.
So I've done a lot of work on my line drawing code and it is improved greatly, and it is now a little bit faster than the BGI for the modes that I've completed. I'm sure I could get it to go a little bit faster if I invested some more time, but I don't know that I have the brain power to manage to do that. I do have one graphics mode left to do, and that's the Visa graphics mode. Basically, I just ran out of time, just doing stuff for my children and work, etc. So eventually I'll get some time and finish that off. I have been doing a little bit of reading about Tandy graphics as well, and I think I might be able to implement that as well, although I think I'll do a separate executable, much like the CGA separate executable I made for XT machines. just because the Tandy graphics mode only supports a small subset of machines, and obviously the sound as well. I think it's totally feasible to write something that supports it. It's more a matter of how am I going to do the artwork for it. So I'm of two minds of either reusing the EGA artwork I already have, but that would force me to use a higher resolution mode, and I'm unsure how the higher resolution mode will work on the Tandy machines. So I don't want to limit it too much, so the high resolution mode might be out. And if it is out, will I write a conversion utility or will I just make new artwork from scratch? Haven't thought that out too much. Might think over it in the holidays that are coming up. But I think that'll be a project after I finish all of what I'm currently doing. Anyhow, I think that's all I have for today's video update. Thanks for watching, and I'll catch you all next time.